Hi, welcome back to Chapter 2, Electrochemistry. We will continue on with Lesson 46, Galvanic Cell, Part 2. Today we are going to learn about how to draw She. What is she? Who is she? The standard hydrogen electrode. We have to describe the method used to determine the standard electrode reduction potentials, the E0 red that we have learned. And then we have to explain the features of the standard electrode reduction potential series, the ECS. And we use the standard electrode potential values to compare the relative strength of oxidizing agent or reducing agent. And we need to calculate the standard cell potential using the E0 red. And then we predict the spontaneity of a redox reaction. What is standard hydrogen electrode? Standard hydrogen electrode is the standard electrode that we use to measure the reduction potential of the other elements. How do we do that? Because we use the standard reduction potential of hydrogen electrode, which is 0. When we compare some value with 0, the value of reduction potential, we connected it with a standard hydrogen electrode, which is defined as 0. We will get the standard reduction potential of that element that we used with hydrogen electrode. So we can see here, the initial of standard hydrogen electron, will be used to measure the potentials of other kinds of electrodes. She is made up of a platinum electrode coated with finely divided platinum. Okay, you can see in the figure there, the platinum electrode is very small at the bottom of the tube. Platinum is expensive, so small mass of it can help become the electrode for hydrogen here. It acts as catalyst also for the half cell reaction, and it will be immersed in an aqueous solution of 1 molar H+ ions. It can be an acid, and it will produce bubbled with H2 gas at 1 atm, 25 degrees Celsius. So this is the description of the standard hydrogen electrode that we're going to use to find the standard reduction potential of other electrodes. What is standard reduction potential? E0 red. It's the voltage associated with a reduction reaction at an electrode when all solutes are 1 molar and all gases are at 1 atm. So as you can see here, the reduction reaction is 2H+ coming from the acid in aqueous form, 1 molar, receives electron, 2 of them. It becomes hydrogen gas at 1 atm. And the E0 is 0 volt. This is for hydrogen electron. Now, here we use standard hydrogen electrode as a cathode. Where is cathode situated? On the right. And you can see the platinum electrode is here. Okay, H2 gas is coming in or going out. And then you have 1 molar of HCl. The H+ must be in the concentration of 1 molar. And then we connected it with a solution of zinc sulfate, whereby a zinc electrode is immersed in it. It is connected with voltmeter. So, as you can see, zinc will be oxidized. It will release its electron, and the electron will flow through the wires and received by H+, producing H2 gas. Here, zinc solid will produce zinc 2+ ion. So, if we can have a reading of voltmeter, the reading of voltmeter is the same as the standard reduction potential of zinc because the standard reduction potential of hydrogen is 0. So it is automatically known that whatever electrode that you attach to a standard hydrogen electrode, the reading of the voltmeter would be the standard reduction potential of the electrode that is attached to it. Okay, let's read the text. Figure 2.5 shows an electrochemical cell with a zinc electrodes and a She, a standard hydrogen electrode. So, the zinc electrode is the anode on the left, where it undergoes oxidation, and the She is on the right, undergoing reduction. There will be a decrease in the mass of zinc electrode because it undergoes oxidation and produces zinc 2+. This is consistent with the loss of zinc to the solution caused by the oxidation reaction. And here is the half-cell equation where we can write to represent the reaction that occurs at anode. The cell diagram is, as you can see, zinc solid becomes zinc 2+ aqueous at 1 molar. You can see that there is a vertical line here in between the two faces, and then this is a salt bridge. Okay, how do you draw the cell notation for She? Now, H+ aqueous 1 molar becomes H2 gas 1 atm. There is one more vertical line here because we did use an extra platinum as an electrode. So, as you can see, this is the cell diagram for the setup that we have discussed previously in figure 2.5. The platinum electrode provides the surface on which the reduction takes place. When all the reactants are in their standard states, the EMF of the cell is 0.76 volt. So EMF is the electromotive force. And you can see that the calculation is anode. That is the half-cell equation, and then cathode reduction. This is the half-cell reaction, and then you can see that this is the overall cell reaction. Zinc solid plus 2H plus becomes zinc 2 plus H2. Okay, and if we look at the, this is called electrochemical equation, whereby you have an E node at the back. Where's the E node? There. The E node for the cell is given by the galvanometer or the voltmeter. The reading is 0.76 volt. But when a hydrogen electrode or standard hydrogen electrode is 0, therefore the zinc is automatically having all the potential, the reduction that is detected at the voltmeter. So this is 0.76 volts. Alright, here you go. This is the formula that we have used to calculate the E naught before this. E naught cell is equals to E naught cathode minus E naught anode. We have the E naught cell from the voltmeter. Then we have the E naught cathode because she is 0. And then this is the one that we want to find. Now, since this is a negative sign, okay, the negative stays here. So the E naught zinc is basically negative 0.76. When standard hydrogen electrode used as an anode, it would be on the left. And now we connected it with copper sulfate. Copper electrode in copper sulfate, connected by salt bridge. So what is going to happen is hydrogen gas enters the standard hydrogen electrode through the tube here, and then electron will be transferred through the wire, producing H plus ions. And then the electron will be received by Cu2 plus, and it would produce a copper solid. So what is actually going on in this galvanic cell? The copper electrode is the cathode. So mass increase during the operation of the cell, as is consistent with the reduction reaction. So the cell diagram would be looking like this, where you have platinum electron on the far left, separated by a vertical line between it and H2 gas. The product is H plus aqueous. Another vertical line is in between them because it's a different phase. Then this is the salt bridge, and then what is the reactant on the right cell? It's a copper ion, and then it will produce copper solid. Okay. Now, this is the calculation of how much the standard reduction potential of copper that we want to find from this galvanic cell. It turns out that the E naught cell for this setup is 0.34 volts. So we insert into this formula here, and then the E naught cathode would be the one that we want to find, and the E naught anode is 0. So the answer for this is 0.34. E naught reduction for copper is 0.34. Let's look at the half cell reaction. You can see here in anode, oxidation reaction occur, and it will produce H plus, whereby at cathode reduction occur, copper sulfate is produced. This is the overall cell reaction. Okay, as you can see, for the overall cell reaction, it must be balanced. So we have 2 H plus here. Okay, the amount of electron is the same, so we cross it out at the upper part and the bottom part. And if you notice in the cell notation, is there any 2 here? No. For cell notation, you do not need to put the stoichiometric coefficients. Okay? Right. This table 2.4 is in your textbook, your course book. So whenever there is a question whereby we do not give you at the end of the question any E naught read for the substance asked, you must refer to table 2.4. Every reaction is there. The more positive E naught, the greater the tendency for the substance to be reduced. It has a higher reduction potential. The half cell reactions are reversible. The sign of E0 changes when the reaction reverses. So changing the stoichiometric coefficient of a half cell reaction does not change the value of E0. Okay, this is an important part. You remember when we do the Hess law calculation, if we reverse the equation, the sign of delta H is changed from positive to negative or from negative to positive. But for E0, E0 is also the same. We change the sign if the equation is reversed. The difference is between delta H and E0. When delta H we multiply by 2 for the reaction, we do it also for the delta H. But for E0, we will not multiply by 2. Now you'll see it later when we do example. What is the standard EMF of an electrochemical cell made of a cadmium electrode in a 1 molar cadmium nitrate solution and a chromium electrode in a 1 molar chromium nitrate solution? Right. So firstly, what we have to do is find the E0 red for both of the substance. So cadmium 2 plus 2 electron becomes cadmium solid. The E0 red is negative 0.4. This is what we get from the table 2.4. And then chromium 3 plus receives 3 electron. It becomes chromium solid. The E0 red is negative 0.74. So we write down these two half cell equation even though we don't know which one is reduction, which one is oxidation yet. So we need to determine which one is going to be oxidized and which one is going to be reduced by looking at the E0 red, because both is at the same situation, reduction situation. So from the slide before this, we know that it says there the higher the E0 red, the more tendency it is to be reduced. And we look at vice versa. The lower the reduction potential, the higher the possibility to become oxidized. So from this value, E0 red for chromium is lower, negative 0.74 compared to E0 red for cadmium, which is negative 0.4. So here we decide that which one is going to be the anode? Cr, chromium. So yes, chromium solid is going to be the anode. It will be situated on the left. It will take its electron out, 3 electron, and it will produce Cr3 plus. And then reduction happens at cathode, whereby cadmium 2 plus receives 2 electron to form cadmium solid. So now what happened is E0 red stays negative 0.4, but E0 anode, E0 ox now is changed from negative 0.74 become positive 0.74, and you can add to get the E0 cell. So what happens here? Oh, this is 3 electron, this is 2 electron. We have to make it the same amount. So all of this will multiply by 2, all of this will multiply by 3, and you will get 2Cr plus 3Cd2 plus becomes 3Cd plus 2Cr2 plus. So notice that this Multiply by 2, we don't have to multiply this one. Multiply by 3, we don't have to multiply this value. This value stays the same. Okay. So now, let's calculate the E naught cell. Here, it used this formula, E naught cathode minus E naught anode. So we have determined that the E naught anode here is negative 0.74. Because we use this formula, we don't need to change the sign. We just insert it in the formula as it is. Negative 0.4 minus 0.74. So you will get 0.34 volts. I hope you understand what is being discussed here in example 2.3. Based on the example that I have explained to you, your task is to do practice 2.3, question number 1, 2, 3. Let's look at spontaneous and non-spontaneous reaction now. Galvanic cell will function when spontaneous reaction occur. For non-spontaneous reaction, galvanic cell will not exist because the reaction does not happen. So under standard state condition for reactant and products, the redox reaction is spontaneous in the forward direction if the standard EMF of the cell is positive. So in order to set up a galvanic cell, we need to predict the E naught cell first. If it's positive, then you can set it up in the lab. But if you calculate, theoretically, it is negative, then your galvanic cell won't work. It will not work. All right. So we are going to look at the E naught cell. Example 2.4, determine whether the following cell is spontaneous or not. Now, it says here that they put stannum as anode. So oxidation will happen at stannum and reduction will happen at magnesium. Look at table 2.4 and it turns out that stannum as anode, oxidation happens, so is going to stannum solid is going to give away its electron to become stannum ion. So E naught red is negative 0.13 volt because it is oxidation. So stannum would be reversed here and this would be positive. And magnesium will stay as it is because this is E naught red. Just take from the table. What happened is, this one we use this formula. So if you use this formula, you don't need to reverse. I like to use the formula E naught cell equals to E naught ox plus E naught red. So that I would do 0.13 minus 2.38. So you just plus or add the formula, the values here. But for this formula, you just add in the ones that you take from the table. So cathode would be this one, negative 2.38 minus negative 0.13, and the answer would be negative 2.25 volts. Now, as you can see here, the value of the E naught cell is negative. Can the reaction occur? No. This reaction is non-spontaneous. This is what you have to write as an answer. Next, example 2.4, question number 2. Will copper metal displace silver ion from aqueous solution? That is, does this reaction occur spontaneously from left to right? Now, I want you to read and understand the question properly, because for the previous chapter, chapter 1, even a simple sentence, construct a bond-Haber cycle for MgCl. That sentence alone, students ask me, what should I do here, madam? I am surprised. What is bothering you? Why can't you understand this simple question? Because the previous sentence said something about Mg2 plus. So we have to find the ionization energy second, right, madam? That person asked me. So you think very far away, but you don't know what is in front of you. You are not sure with what is in front of you. Construct one Haber cycle for MgCl. That's it. This is a different chapter. Okay, what I want to emphasize here is understand word by word, sentence by sentence. Will copper metal displace silver ion? Meaning that will copper metal exist and will silver ion disappear? So it means that will this reaction occur? So we need to find the E-naught rate for both of these elements. And here is it from table 2.4. Copper, this one, it is already reversed. So originally it is 0.34. Now it is reversed because it is oxidation. Negative 0.34. And then reduction, this is a reduction state, 0.8 volt. So now this is using the formula that I like, E-naught red plus E-naught ox. You can like whichever formula that you want. Madam Tipah likes the formula from previous example because it comes straight from the table. But I would like to reverse this half cell reaction because if the question later comes, write the overall reaction, cell reaction, I already have the half cell reaction here. So it would be easier for me to answer. Therefore, here I put E-naught ox because it is reversed. It's not 0.34 anymore. It's negative 0.34. Add in negative 0.34. And then when you combine it with 0.8, which is higher here, the reduction potential is higher in argentum, in silver. So the answer is 0.46 volts. Now, you can answer the question now. Copper solid now displaces argentum ion or silver ion in the reaction. So, meaning that copper solid, will it become copper ion? Yes. Argentum ion, will it disappear? Yes. The reaction here is spontaneous because E-naught cell is positive. That's all. Thank you very much, boys and girls. I hope you would understand what I've been talking in this lesson 47. And let's continue the journey for semester 2 together. Pay attention, do your job well, and stay safe, everybody. Thank you very much for watching. Assalamualaikum warahmatullahi wabarakatuh. Madam Ruby logging out for lesson 47. Thank you. Bye.